Hello, welcome back. I hope you are all learning a lot from the previous sessions and you are revising yourself and looking into learning about different concepts by now, knowing about the architecture, about the bus, what are all it's involved, and also the different registers and how they are used, and also how the address offset is being used. And you might have practiced how to blink the LED and the control of the switch. And welcome back. And today is day 9 on embedded system on ARM Cortex M4. And today we're going to learn about understanding the stack memory. Stack memory plays a vital role in embedded programming. This is where you stack your addresses into a particular location. So that's where stack memory comes into play. These are all the sections you will be learning today. You're going to learn about what is stack memory and what is it all about and where they are all used, and the different stack operation modes. What are all the different stack operation modes there are and how it is used into learning with the program. And also stack placement. There are various ways of introducing the stack placement, so you will get to learn about it, and also the demo about how this stack is in real operation. You'll go through step by step understanding about it, about how the stack is used in your program, and then you will jump into learning about what is a function call and what is AAPCS standard. There is a standard which is used for function call. AAPCS stands for ARM architecture program call standard. And then you will learn about different stack activities, what happens when an interrupt or an exception occurs. These are all the sections you will be learning today. I'm sure at the end of the session everyone will be more familiar about stack memory, and also by learning today you will be also familiar to answer any sort of questions that comes with stack memory, because this is an important topic and you will get more questions in an interview point of view because you need to know how the stack operation works. So let's get in and see what today unfolds for us. Before jumping into the main study, I would like to say a few words about whom I am representing. I am representing A2DG. It's a startup by Anbukarasu brothers. My brother Alex and myself Farul started in 2023. Both of us gathered over 20 plus years of experience and knowledge. Over those years we gained a lot, and we would like to express that and share that with you all, so it will be all helpful to you, so that you can be building your way into becoming a better professional engineer. And our mission is to convey those experience and knowledge to at least 100,000 future professionals out there through the form of online courses. The good benefit out of this is you can study anywhere at your own time, at your own pace, wherever you are. You don't have to go to a class. You can sit even in a park. All you have to have is internet and our course series, and you would be able to learn. So that's the main advantage. About me, I am Arul Prakashan Bukarasu. You can call me as Arul or API, as popularly as I'd like to be. Jokes apart, sorry. I have 20 plus years of experience working in Australia. I came to Australia back in 2003, doing a major in master's degree, majoring in embedded systems and VLSI and in project management. Since then, I've been working here in various industries, starting with the renewable energy sector, concentrating on solar and wind energy system, power systems that dealt with lead acid batteries, the network embedded systems that were dealt with automatic teller machines, the teller cash registers, the point of sales, and the banking automation systems and smart parking operations. So I went through the whole development life cycle during the last 20 year span, and I would like to share my experience and my knowledge to you all, so that you would also be very focused on becoming a better professional engineer in the end. I got small announcement to make. I categorized into two different categories as YouTube viewers and internship professionals. for YouTube viewers, you have to go into my channel A2DG, and all the video sessions will be loaded there. In order to be eligible to get an e-certificate, you have to attend at least 28 classes. There will be an attendance link, um, will be linked with that particular video. So after you finish watching the video, go back and click on that link, and you can fill in your details, and that covers you for your certificate attendance. As part of YouTube regulations, the videos can't live there forever, so after 2 or 3 days it has to be removed. So if you miss a class, or if you can't understand, if you want to go back, you can't access if you want to go back, and so therefore you have to be there every day to learn. So that's why I personally recommend you and advise you to join our internship program. So what do the internship professionals get? They get to acquire their internship certificate. As I keep saying in the previous sessions, that's worth a lot. When you get into the interview, or after you got the job and you're working with the team, your senior engineers and product managers would consider that as a lot of effort that you put in to get into that stage. Because as a beginner, when you join into any company, at some stage the senior engineers and the managers have to train you first, to show you the tool, or a bit of a logic, etc. But they would see this as you invested already, and you know the system, and you know what to do, so they don't have to tell you much apart from saying this is the project, go and do it. So you would be able to be there and do from day one. And what would this internship will give you is, it will give you a separate login, so that you can log into the learning management system portal, and you can go through our daily recorded session of the videos. And once you complete one section, you have to click on complete and continue. That will cover for your attendance. So this attendance will be evaluated to provide you an internship certificate at the end. Not only that, you will get unlimited access to all our course contents that's listed in there, and also unlimited access to course content videos. So you can pause, you can restart, you can forward, you can come back and watch it again. So that's a big benefit. And if you get stuck anywhere in the process, please reach out to our backend team, and they are a very friendly team, and they would be able to guide you to move you further along with the course. So now let's get in. And these are all the materials you need to have your start to have your hands-on experience. So that counts a lot in the industry, as you already familiar with the IDE installation and IDE setup and etc., and how you interface with the board. These are all the big plus points that the interviewers or the engineers whom you're going to work with will consider us, because I learned the hard way going in, and fortunately I got the senior mentors, so I was able to understand and read and learn from them. But I'm making it easier for you by advising you to collect all these materials beforehand. So please contact Pantex Solutions. They are a big manufacturing company, and they would be able to help you to acquire all of this. So you need an STM32F11 RE nuclear board, and a logic analyzer, the ESP8266 sensor circuit, DSTL Wi-Fi module, a DSTL 11 sensor, ADXL 345. So these are all will come in handy in some sessions. So you need to have all of this. And please contact Pantex Solutions. They would be able to help you to get all of this. And for today's session, these are all the documents would help you to understand further more in your learning curve. You need to have the STM32F411 datasheet. You need to have STM32F411 reference manual. You need to have Cortex reference manual, and you need to have AAPCS standard. That's the standard used for ARM architecture. It's a procedure called standard. You can either Google and download all of this. If not, then I have loaded all these documents in the Facebook group that I will mention later. And you can download from there. So these are all the must you need to have, so you'll have a better understanding to follow up with this class. I'm sure you are keen as I am, so let's get started before not wasting any time. So let's get into it. What is a stack memory? introduction about it. As you know, in any microcontroller or in any embedded programming, there is basically two types of memory. There is a read-only memory and there is a random access memory. Read-only memory is non-volatile, and that's where your program initial data sits in, and random access memory is where your data sits in. So it is a volatile memory. So when it loses power, it will lose everything. And stack memory is a part of an internal RAM or external RAM reserved for temporary storage of data. So it's nothing, stack memory is nothing but where you allocate somewhere to temporarily store the data, the transient data, and you can use that data to use it for some other purpose in the program. So that's where stack memory comes in handy, and it can be placed in either internal RAM. The STM32F411 comes with on-chip 128 kilobytes internal RAM. You can use that, or you can have an external RAM. You can connect it to the board via the pins, and you can also store it in the external RAM. Stack memory are mainly used during the function call, or it can be also used in interrupt or exception handling. So when there is an interrupt, you can also use that to the stack memory. And the stack memory is accessed in this fashion: last in, first out. So whatever data comes as last in the stack memory, that will be retrieved out as the first out fashion. So this is how the stack memory in ARM Cortex M4 series or this microcontroller works. And the stack can be accessed using two special instructions called push and pop instructions. Use push instructions to store the data and use pop instruction to retrieve the data. So that's where the push and pop. Or else using any other memory manipulation instructions like load register and store registers also, you can access the data that way. LD stands for load, STR stands for store. And when you point your addresses into the stack memory, you can address that stack, and you can also trace that stack by using a special register called stack pointer, SP register. So this is where in the programming register, if you use stack pointer, it will allow you to pinpoint the location of the addresses where it is. So that's where the stack pointer is used. And with the help of push and pop instructions, when you do store and retrieve data, it affects the increment or the decrement of the operation in the stack pointer. So you will get to learn that in the next coming slides. So that's what you will understand more about push and pop. And the stack pointer will show you the current stack pointer location, and that will be the R13 location that you will learn in the next one. Okay, so where the stack memory will be all used. As we learn from the definition, stack memory is nothing but it's where the location where it has a temporary storage of data of its variables for a processor register value. So all the register values will be stored in a temporary location, and that will be called in a function call to use it. So that's where stack memory is. So the temporary storage of local variables of the function. And during a system exception or an interrupt, stack memory will be used to save the context of the current executing code via general purpose registers or process status registers and a return address. So via all these, the stack memory will be loaded. And depends on the case, the stack memory can expand or shrink during the runtime of the program. So you can actually set the start address and the end address, so you can expand. Also, if you want that special register to be used for other usage, you can also make it shrink. So that's what it explains. The stack memory can be expanded or shrinked. Now let's try to understand just by a simple program. This is a generic stack memory you have in a program. Take any C program. So the main prints the sum of A and B. The main program, main function, its point is to store the values of A and B in the addition format. So that's what this program explains. As you know, in the stack memory, so these are all the various links that you have to understand. The stack memory comes with low address. It starts with the low address and it has the high address. And first off, in the low address, you have a dot text code, and that's where your program and the startup code, everything will be in the dot text. And after that, there is the BSS locations where the data is categorized into the initialized data and the uninitialized data, and there is the heap. Heap is nothing but when sorry, just one sec. Operation model heap. Um, Heap is nothing but when sorry, I got interrupted. Heap is nothing but when you allocate to a memory allocation dynamically. That's where heap, you have to use the heap instructions, and this is where the stack is always placed on top of the instruction level. So that's the heap and that's a stack, and all your arguments value are stored in a stock frame. When I say argument, like the int a comma b, that's an argument, the sum is an argument, so they're all stored in the stack pointer via a stack frame. So this is how a stack memory works in a program. And shortly, I'm going to explain to you how the program you're going to write and how the stack works in there. Okay, now let's understand about stack memory. So in the SRAM memory that we are learning, the stack memory will start, the SRAM will have a starting address and an ending address. As I mentioned earlier, your STM32F411, this series, the program, the board has a built-in 128 kilobytes of SRAM. So one part of the SRAM is used for global data, where you store the global data, so it can be static local data or instructions. The other part of the SRAM is reserved for heap. As I said earlier, heap is used for dynamic memory allocations, when you dynamically allocate some locations for the memory storage. And then the other part of the STAM is reserved for stack. So this is where the stack will live. This section is utilized for any function call where you can save the data and store it in a temporary location in the stack frames, and during interrupts and exceptions you can go to that exception or interrupt case, and then you can come back to it. So that's where the stack comes in play. It comes with the start address and the end address. Now let's see what are all the different operation models. There are basically 4 stack operation model out there. What are they? They are all full ascending stack, it's denoted as FA, full descending stack denoted as FD, and ARM Cortex M4 follows the full descending stack. And there is empty ascending stack denoted as EA, and there is the last one, empty descending stack, which is denoted as ED. For example, consider this in the stack pointer in your stack memory allocation. So this is to explain about the operation model. And picture courtesy to Serial Labs, it made my job a bit easier, so I can understand much better and also make you understand a lot better. As I said earlier, the stack memory by default comes in as an increasing address. So by default it comes as a full ascending address, full ascending operation model. What that is, the stack pointer will point to a location, and you have to push the data to the location, and then you have to increment the data. So that's what this is understanding about the link. So when a function call happens, this stack pointer will go to that function call. So maybe it is a exception or a handler. It will go and do that job or whatever it's asked to do from that function, and the stack pointer will return back to the stack pointer. So in the full ascending operation model, the starting address, it will go from low to high. That is 000 to 0FF. That's a full ascending. And the full descending is Cortex M4 is a full descending mode, where it's the opposite. The stack pointer will be accessing from high address to the low address. So it goes from the other way. The instead of from low to high, this goes from high to low. So now the stack pointer is on 8. So the next one, it will be 9, 10. Instead of descending, instead of ascending from 0, 1, 2, 3, this goes from 8, 9, 10 like that. And then the third operating model is empty ascending model. Empty ascending model, it shows first the stack pointer will be sitting in a location, and then you will push the data. That's the difference in first you're loading the data and then you push that to store. So you're allocating the location first and then pushing the data to store. And the empty descending is exactly opposite to empty ascending. And still you let the stack pointer to know where it is and then push the data, and this happens in the reverse order. The higher address gets in first and then the lower address. And our Cortex M4 series follows the full descending operation model. Now let's understand by a small operation model ARM Cortex M4 through this small stack level diagram. And picture courtesy to Pantech Pro Labs, they explained it really well, and I thought I would be able to use that and explain it to you. It's always about the increasing memory address, as by default the operation mode is in full ascending, but in Cortex M4 series it's full descending. So this is what happens. You push the linker file in there, so they're all previous data all pushed to the memory location, and you use push and pop instructions. The push is used to store the data and pop is used to retrieve the data. So you're pushing the first argument R0, then push R1, that's the data, then pop R2. So what happens in the core registers of the processor, the R0 will have this value because we asked R0 to push first, so it goes in the descending order. So it goes first like that, so it comes down. So when you use the pop R2, then initially the data will be 0, or for example the data on R3 will be 5. So as soon as you ask pop R2, so it retrieves the last data. So this will be here in R2, 0 cross AB11. As you know, this works in live-off fashion, and then if you use pop R3, then the next one comes out, FFBC, and then pop PC comes out. So PC is a program counter and that's a linker. So this is the stack operation model in ARM Cortex M4. And now let's understand a bit about stack placement. There is two different types. There is type 1 and type 2. In type 1, as you can see, this is the increasing memory address, and the type 2 is where the full Cortex M4 we uses. The data first stored in the tab, and then the heap start address will start at the end of the data address, and this is where the stack lives. The end of the heap address will be in general the full ascending. This is the format they use. So they have the stack start and the stack end, but the type 2 is what full descending on ARM Cortex M4 is. So in this type 2, the stack is coming from higher level to lower level, so it's pushing from 0FF to 0 cross 0, 0. So you have the stack start and stack end, and that's pushing down, and that's where the heap start address is. So the difference between the type 1 and type 2 is nothing but This follows in ascending format and this follows in descending format. So that's why there is a gap to show how the stack is being pushed down and how it's placed in the descending format. Now let's try to understand about the banked stack pointers. In Cortex M processor, it has 3 pointers, as most of you would know, and again, big courtesy to Pantech Pro Labs. Always the current stack pointer. In every program, it will show the current stack pointer, and it's the pointer register, a special register called stack pointer, and R13 is a stack pointer. Inside R13, there is 2 different stack pointers. One is the main stack pointer and there is a process stack pointer. So these 3 are the banked stack pointers, and we will be learning shortly about how the current stack pointer changes to main stack pointer and how it changes to the process stack pointer. Now let's try to understand about the operations mode of the processor. As from section 3, you would have learned about there is 2 different modes when you write the program. The processor will handle in thread mode or it will operate in handler mode. The thread mode is also called as a user mode. All your application executes normally on a normal program first executes in a thread mode. Only when an exception or an interrupt occurs, then it goes to that handler mode to assess that and finish that and then return back to the thread mode. So the processor always starts with the thread mode. Whenever an interrupt occurs, it changes to handler mode. So that's the operation, how it behaves in the program. And there are 2 different levels for the processor to access. There is PAL and NPAL. What is PAL? PAL is privileged access level. So if your code is running with this PAL, then there won't be any restrictions, meaning your code will have full access to all the restricted registers that's used in the processor specific resources. That's what the privileged access level is. And the non-privileged level, if your code is running in NPAL, then the code may not have full access to every register. There may be a restriction due to some functionality changes. So by default, the code will run in PAL, and you have the option to choose NPAL, but you have to write a small code to change from PAL to NPAL, and that's what it will happen. And in general, with the handler mode, code execution is always at privileged access level. And if you want to change to non-privileged, then again you have to write a small code in handler mode, and that tells the processor to change from PAL to NPAL. So this is about the different access levels, the privileged and the non-privileged. Now let's briefly know about stacked pointers, banked stack pointers. So once the processor resets, whatever on the MSP, the main stack pointer, will be selected as the current stack pointer location. So it means the stack pointer copies whatever the contents, whatever the address, whatever the value the main stack pointer has, that will be showed in the stack pointer on the current stack pointer location. So in other words, you can't change anything. Whatever is on MSP, it will show on the stack pointer. Then the thread mode had to change from stack pointer to PSP. If you want to use a processor stack pointer, then there is a control register called SP select bit. You need to set that bit to 0 to access to MSP, and if you set this bit to 1, then your stack pointer will know that it's going to get value from your PSP. And the handler mode code execution will always use MSP as the current stack pointer. Changing the control register SP select has no impact in the handler mode, because by default it sits with MSP. Whatever you change in the control register, it won't impact the MSP. That's what it this point says. And the MSP will be initialized automatically by the processor after every reset by reading the whole content of the address, and it will reset, and the address will go back to 000 and 000. So this is to follow with the previous slide. When you set the SP select 0, the stack pointer will know that it's going to retrieve or it's going to send to the allocation of MSP, the main stack pointer, If you set the SP select as 1, then the current stack pointer will denote the location to process stack pointer. So whatever value you have there, and that will be pushed to the stack pointer. So this is the two different control bits. With 0, it acts and denotes to the MSP. With the SP select as 1, it goes to the PSP. So now let's get into a demo. I'll show you a short demo to make you understand how this stack initialization works. Before that, I'll give you a bit of a briefer, so please go and have a bit of a rest and have a bit of a breather. Come back in 5 minutes, then I'll show you the program and you will be able to learn more. Thank you. I'll see you back shortly here. So don't go far away anywhere. Please come back. I'll show you how it works in the IDE. So see you back shortly.